Okay, good afternoon, everyone. Welcome to this, the latest in the Infrastructure Transition Research Consortium webinar series on net zero energy and transport. It's great to see so many people participating. We've got 70 participants so far, and there are still more people being let in. And I think that reflects what an interesting topic this is we're talking about today. My name's Jim Hall from the University of Oxford, and I'm lead the Infrastructure Transitions Research Consortium. And this webinar series, welcome back to those of you who've been with us previously, is really the culmination of almost 10 years of research by ITRC, developing, with the support of the Engineering and Physical Sciences Research Council, modeling and methodology for analysis, planning, simulation of national infrastructure systems. You can see the lineup of the webinar series in front of us here. We began on the 29th of September with an overview of all of the systems analysis which the ITRC has developed. And then since then, we've done deeper dives into different aspects of the research. On the next webinar on the 6th of October, looking at downscaled analysis we've done for the Oxford-Cambridge ARC. And then on the 12th of October, looking overseas to the uptake of the ITRC's work for infrastructure planning for international development, because of the fundamental role that infrastructure has in countries' development and the Sustainable Development Goals. And then in this webinar, we're focusing in on one of the key interdependencies in national infrastructure systems. And interdependencies has been more or less the raison d'etre for ITRC. We've developed system of systems methodologies. So looking across energy and transport, which are the two systems we're looking in this webinar, also incorporating water, digital communications, both fixed and mobile, and waste. And we've developed modeling methodologies, and you'll hear a lot about that today, to represent the future of those systems, the ways in which they might evolve, what are the options, and how might those options perform under a range of different future scenarios. And we've learned a lot about interdependencies in going through that process. And what has come out of this is that the interdependencies between energy and transport in the future are going to be huge, because, as we all recognize, of the role of primarily of electrification, and possibly also of hydrogen. And when you look at that, you quickly get some sense of what the potential scale of electricity demand from the transport sector might be as we electrify the transport sector on the pathway to net zero. But you don't have to think about that much for very long to recognize there are a whole series of additional complexities to do with the variability of renewable electricity supply because of the variability in wind and solar. So the need for storage or backup on the electricity grid, and then the role that vehicles might have in terms of optimizing when they charge or using their batteries as a vehicle to grid discharge mechanism. And you can already imagine that analyzing that properly is a complex task. And then on top of that, we have the fact, as I've already mentioned, that there are actually some very different technology pathways which we might go down via electrification, or to what extent is there a role for hydrogen within this setup. And the cost questions there, the technological and behavioral uncertainties, and there's a great deal of path dependency. And we're going to explore all of those in the webinar today. I should emphasize that we don't have all of the solutions. Our speakers are going to be Madassa Chowdhury from the University of Cardiff and Simon Blaney from the University of Southampton, and they'll explain some of the analysis that we've done and some of the answers. But part of what we're showing here is the platform of capabilities that exist to analyze these extremely complex problems. And in order to do that, you need a deep systems understanding. That understanding needs to be spatial. So we need to know where vehicles and traffic and renewable energy is and is coming from. It needs to be coupled, but it also needs to be computationally tractable so we can explore the wide range of possible futures. So we're going to start with presentations from Madassa and Simon. And then we're going to get feedback and remarks from Alec Waterhouse, who's head of modeling at the Department of Business, Energy and Industrial Strategy, and Siobhan Campbell, who is head of the Central Research Team and Deputy Chief Scientific Advisor at the Department for Transport. And then from Eyre, who is director of the Centre for Research on Energy Demand Solutions, another large UKRI program. And we're most grateful to all of those speakers for sharing their time with us. Please let me skip back up to this. Tweet if you feel fit. Follow us on LinkedIn, and the video of this will be available on YouTube, and we will make the slides available after this webinar, so you can share that with people who haven't had a chance to join us. We'll be taking questions after remarks from our speakers and respondents, so please start to put your questions in the Zoom chat as soon as you like, and I'll share that discussion and hand your questions over to the appropriate speakers. But keep them coming, and I will fire those through to our speakers. But without any further delay, thank you all again for joining us. We now have 94 people with us, and I will hand over to Madassa Chowdhury from the University of Cardiff to present this work from the ITRC. Over to you, Madassa.
Okay, let me just get straight into it then. So we all know that the UK has legislated for a net zero carbon emissions target for the whole UK economy by 2050. You can see on the left-hand side of the slide some of the key documents displayed, especially the one from the Committee on Climate Change. This was essentially the analysis that framed the discussion on potential pathways. One second. Bear with me. I've been asked to do something here. Yeah, so this is the analysis that framed the discussion and potential pathways in which the net zero target could be met by 2050. So this essentially requires a power system that is decarbonised, alongside what some people have described as one of the biggest challenges, decarbonising the heating sector. So what makes heating so difficult is the sheer number of buildings that you would need to decarbonise, whether they be domestic or commercial, and potentially we have a number of different heating technology options that can be used to decarbonise the sector. Alongside this, we need the transport sector to play a leading role in the push for net zero emissions. Transport is now the largest source of carbon in the UK. So as we push into the next decade, road transport in particular will need to switch to low carbon alternatives. So in our research, we investigated the impact of distinct heat and transport strategies in the context of the net zero target. So to perform the analyses, we use the NISMOD platform and the complete set of sector models. In particular, what you see in this diagram are the high-level interactions between three key models: the energy demand, transport, and the energy supply models. Now, within the energy demand model, characteristics such as population, temperatures, floor area are all used to determine heat and non-heating demand using a simulation approach. And likewise, in the transport model, also provides outputs such as energy consumed by road transport, and through a V2G module, the magnitude of electricity or electric vehicle battery capacity available at a particular time and location is also determined. Now, on the outputs, now we have the outputs from the energy demand and transport model alongside some of the characteristics that you'll get from variable renewable generation, which is determined by a detailed weather module. All of this feeds into the energy supply model that determines the optimal approach in operating the energy system given a particular infrastructure strategy. So that's how, at a high level, how the three models actually work together. Now, in terms of the energy supply model, we have a whole energy systems model, which includes characterization of energy supply systems at both transmission and distribution scales and across multiple energy vectors. The model performs operational optimization, where operating costs of the entire energy system are minimized. So the diagram you see on the left just essentially illustrates that we have modeled the transmission system. So this is natural gas and the electricity networks. We model all the resources such as gas, transmission elements such as gas terminal, pipes, generation technologies, and the interactions with the electricity transmission system, and finally the connection with the distribution systems are all modeled. We employ the energy hub approach to model energy distribution systems. So this essentially allows us to encapsulate some of the key interactions across multiple energy vectors within local energy systems. Additionally, we have various functional modeling capabilities such as bidirectional energy, electricity interconnector flows, which can either be balanced or unbalanced. We have demand side management capabilities, and of course we model intermittent renewable generation. So before I dive into the energy supply options and strategies that we modeled, my colleague Simon will give you an introduction to the transport models, some of the low carbon road transport options, and some of the outputs of the model. Simon.
Thanks, Madassa. Okay, so I'll give you a brief introduction to the NISMOD road transport model and then explain how we used it in this work. So the NISMOD road transport model is a network model covering the entire Great Britain major road network, which you can see just about in the map on the left there. And it's calibrated with a base year trip matrix, which is based on observed traffic count data. So it represents traffic in the base year to start with. It then simulates change in traffic levels for all of these flows over time in response to changes in the values of a range of different explanatory variables drawn from the different elements of NISMOD or pre-specified by the transport model. And the particularly important one here is energy cost. It also incorporates feedback between traffic levels and the travel time and cost, and iterates between those two values up to a pre-specified limit. If you're doing any run with the transport model, you need to pre-specify values for a range of what we call scenario variables at the start of the run. So you have to say how you think these things are going to change over time. And the two variables which are particularly relevant here are road vehicle fuel efficiency and particularly changes in the fuel mix of the vehicle fleet. You then, once you've specified all the variables that you're interested in, run the model and it will produce outputs against a range of different KPIs, with again the particularly relevant one here being energy consumption. So next slide, please, Madassa. So for this piece of work, we have assumed that transport will be decarbonised, which isn't necessarily automatically the case. We might want to flick back a little bit there, but I'll keep talking. So the two strategies we are looking at here look at different possible energy mixes for the road vehicle fleet, which will lead us to a decarbonised future. So the first of these we've called full electric. As the name suggests, that involves the complete electrification of the vehicle fleet, with a ban on the use of conventionally fueled vehicles around the middle of the century. Whereas the second strategy, electric and hydrogen, sees hydrogen emerging as a major competitor for electricity in powering road vehicles, so that by 2050 you have got a fairly even split between the two fuel sources powering the road fleet. Now, we'd also consider changes in a range of other factors such as population up to 2050 in our model runs, but these are the same for both strategies. So the differences you will see between the strategies are driven by the changes in the way in which the vehicle fleet is powered. Next slide, please. So I've just briefly presented some of the key outputs from the model here. So on the left, we've got total vehicle kilometers for different vehicle types, first of all in 2015 and then in 2050 with our two different strategies. And you'll see that the full electric strategy has a substantially higher level of vehicle kilometers than the mixed hydrogen and electric strategy. This is primarily because electricity is assumed to be a cheaper fuel. The cost of travel is therefore lower, and therefore people travel more. Related to this, on the right, you can see a measure of congestion. So this is showing the average link travel time as a proportion of the free flow travel time. So if that value is greater than 1, then that implies that there is some level of congestion. And this is modeled for two different time periods, the morning peak and the quietest hour in the middle of the day. And you can see again that congestion levels are substantially higher with the full electric strategy. And this again is because travel is cheaper, so people will try to travel more. The growth compared to 2015 is also driven by the substantial population growth which has occurred over that period. But it's worth noting that if you do change from a high tax fuel to a low tax fuel, so petrol and diesel to electricity and hydrogen, this is likely to have a substantial negative impact on congestion unless you do also take parallel steps in terms of transport demand management. Next slide, please. So this then is looking at what the impacts are in terms of transport energy consumption. So at the top, we've got the base situation in 2015, a vehicle fleet powered almost entirely by petrol and diesel. And in comparison below, we have our two future strategies. And again, you can see some substantial differences here. As you'd expect, with the full electric strategy, nearly all the fuel consumption is of electricity, whereas on the right-hand side, electricity consumption is substantially lower, but hydrogen is now quite significant. And again, these futures would have quite significantly different implications, particularly in terms of fueling and charging infrastructure. You would need a very different system of supporting infrastructure with the hydrogen electric strategy as opposed to the full electric strategy. Back to you, Madassa.
Thank you, Simon. So Simon has laid out the two road transport options. Now, on the energy side of the equation, especially around the all-important area of heat decarbonisation, it's generally recognised that no single heat technology can provide the best solution for all users. So a mix of technology options will need to be deployed to cater for differing consumer requirements. So to complement the work performed by the CC and others, we have two contrasting heat decarbonisation options summarised in the table above. We have the electrification pathway, in which we have technologies such as heat pumps, resistive heating, and electric boilers. And we have a multi-vector pathway, in which we have widespread uptake of hydrogen boilers in combination with other technologies such as heat pumps and district heating systems supplied by biofuels and hydrogen. Now, the combination of the heat and transport options are used to define the following four wide-ranging strategies shown in the diagram on the bottom left, where we have electrification of heat and transport, all elec. We have electric heating and a combination or a mix of hydrogen and electric transport, and two multi-vector heating options combined with a combination of hydrogen electric and all electric transport. So we have one full electric strategy and 3 differing levels of multi-vector combinations for heat and transport. Now, across all these strategies, we apply managed and unmanaged charging, and we can enable vehicle-to-grid supplies as well. So the energy supply model was used to explore the impact of decarbonising heat and transport on the GB energy system operation. So let me go through a few selected results. So now on this slide, the diagrams illustrate the heat and road transport input demand at the top and primary energy supplies on the bottom for 2015 and for all the strategies in 2050. And this is considering unmanaged charging with no V2G services. What you can see straight away is that the input demand for heating and transport in 2050 across all strategies is far lower than in 2015. This is due to a number of reasons, such as efficiency improvements within homes and in transport. So despite increases in population, we see quite a large reduction in overall heating demand and transport demand. Now, in terms of the strategies in 2050, the all-electric strategy has the lowest overall heat and transport input demand. This is mainly due to the efficiencies that we expect from heat pumps. The strategies where hydrogen is required for heating will require higher demands, as hydrogen boilers don't really compare with heat pumps from an efficiency perspective. When transport is added, the requirement for hydrogen can rise to as high as 400 terawatt hours in 2050. But the overall story is far lower demand requirement in 2050 than 2015. The diagram on the bottom shows the annual energy supplies. It essentially mirrors the demand diagram above. Annual energy supplies in all scenarios in 2050 are lower than 2015 across all the strategies. And in grey, you can see the gas supplies. Gas supplies decline in all strategies, 80% lower than 2015. And where hydrogen plays the role in heating, the decline in gas isn't as profound, as steam methane reformation is used to produce hydrogen. Now, you can see that electricity generation, and this is a primary source of electricity generation, so wind, solar, hydro, nuclear, and imports, virtually doubles in the strategies in 2015 compared with 2015. So around 600 terawatt hours to meet heat and transport demand and production of hydrogen through electrolysis. We currently have a peak of around about 51 gigawatts on the electricity system. This increases to potentially around 120 gigawatts in the all-electric strategy. Now, renewables play a large part in the provision of energy in all the strategies. The contribution of renewables is approximately around 400 terawatt hours. We have around 150 gigawatts of renewables in the system by 2050. Now, with all that capacity, there's going to be curtailments, which are highest in the electric, all-electric strategy, around 35 terawatt hours. Okay, so that's unmanaged charging. So what happens when we have managed charging and V2G services? Now, the diagram on the left illustrates the electricity generation over 24-hour period during a winter's day. The top diagram is the case with unmanaged charging and no V2G, and the bottom diagram is a corresponding case with managed charging and V2G. Both diagrams are for the all-electric strategy. The blue lines that go across the time series show the charging regime. So with managed charging and V2G services enabled, we see a reduction in demand during peak hours. Currently, this period is around from 1800 to 2000 hours. This is highlighted in the red box, of around 30 to 35 gigawatts. And in the bottom diagram, when you see the V2G services and the shifting of this peak demand occurring, you see a overall reduction of around about 10 gigawatts. So these actions have other impacts, such as reduction in use of gas-fired generation. We have a reduction in emissions, and we have greater utilization of wind and therefore less curtailments. And the diagram you see on your top right-hand side shows the annual reduction in curtailments for when managed charging and V2G services are used for the all-electric and the multi-vector strategy. And in both cases, you see big reductions in curtailments of up to around 8 terawatt hours. So with this flexibility, managed charging and V2G services, we show this could potentially reduce operational costs in the range of £2 to £8 billion annually in 2050. So on this slide, we look at the impact of wind variability on system operation, and in particular, how the system operates during periods of low and high wind in the all-electric strategy in 2050. Now, the diagram on your left-hand side shows a day in which we have low wind with unmanaged charging. Diagrams on the right, we have the managed charging cases, where the top one is the low wind case and the bottom one the high wind case. And what we observe is that when there's a significant drop in wind and it coincides with peak demand, you can see increases in gas-fired generation. So this is CHP and CCS, increases in imports. We have grid-scale battery, which is discharged to make up for low wind generation. So even though that the system is operating in that we don't get loss of load, we get higher operational costs and emissions. Now, when you have managed charging, which is top right-hand diagram, EV charging is essentially shifted to periods when there's plentiful wind generation. And of course, this increases utilization of renewables. In the high wind case, we essentially see greater charging of grid-scale battery storage and generally more EV charging whenever there's a ramp up in renewable generation. In multi-vector strategies, one of the key features that you do see is a shift in how hydrogen is produced. So in low wind cases, we see more SMR to produce hydrogen, and the reverse is true in high wind cases, where wind generation is used to produce hydrogen through electrolysis, and in the process, we get a reduction in wind curtailments and costs. So on to the final slide. Here we show the annual energy system implementation costs, which are undiscounted for year 2050. So for all the strategies, so the bars in the diagram are separated by capacity, which is in grey, and includes items such as generation, heat technology capacity, and hydrogen production capacity. We have operational costs in orange, and then we have network costs in blue. So the bars represent system costs without smart charging, and the black dash that you see is the total combined cost with managed charging and V2G services. What you can observe is that electrification of heat strategies have the lowest overall implementation costs, mainly due to having lower power, heat, and hydrogen capacity and network capital costs. Interestingly, the electric heat capacity with a mix of electric and hydrogen transport has the lowest overall system costs at around £58 billion. And this is assuming no smart charging and V2G. And this is mainly due to lower operational costs when compared with the all-electric strategy, which has no hydrogen production. So excess wind power generation is used in the production of hydrogen through electrolysis for hydrogen transport, which further reduces operational costs. Now, costs associated with power and heat and hydrogen capacities are largest in the multi-vector strategy. This is mainly due to use of expensive CHP systems and the requirement for hydrogen production capacity to meet heat and transport demand. Now, network-related costs in the multi-vector heat strategies are 60% greater than the electric heat strategies. This is mainly due to the implementation of heat networks, where costs related to civil engineering works are quite high, and of course the cost of building a new hydrogen network, even though some of the gas pipes are repurposed. Given greater number of EVs and electrification of heat, the implementation of smart charging and V2G has the biggest impact in reducing total annual costs in the all-electric strategy of approximately 16%, so lower operational and capital costs. So from an implementation cost perspective, the all-electric strategy and the strategy with a mix of electric and hydrogen transport are shown to be the best. But we do have to remember that operationally multi-vector heat solutions are quite competitive. And with learning by doing over time, we could see reductions in the assumptions for capital costs of CHPs, hydrogen production technologies, and heat network costs. And finally, I'll end with stating the obvious, that before attempting any technology solution, we need to double down on energy efficiency improvements within homes. It really is a significant low regret solution. Jim, I'll end there.
That's fantastic. Thank you very much indeed, both Madassa and Simon. If you could stop sharing your screen there, Madassa. We've already got a whole bunch of questions coming up in the chat, and I've been noting which of those are for Madassa and Simon, so please have a look through the chat now and we'll begin to pick up on those. And by all means, continue to put your questions in the chat. But before we do, let me first pass over to Alec Waterhouse. Alec, thank you very much for joining us once again from the Department of Business, Energy and Industrial Strategy, for some insights from your perspective within government. And if you don't mind, there's just one question I picked up from Ash Gupta around the regulatory implications for DNOs and the need for DNOs to invest. And Ash is making the point that is not being permitted to a sufficient extent by Ofgem. So that's clearly a question for regulators, but over to you, Alec.
Okay, thanks very much. Can you hear me all right, Jim?
Yep.
Okay, just saying thanks to Tim and Madassa for what I thought was an absolutely fascinating presentation, and it's really interesting to see the work of a sister group of modelers working on there. By way of introduction, I head up the central modelling team within the Department for Business, Energy and Industrial Strategy. We hold some of the larger scale models that government uses to think about energy and decarbonisation policy. And I was very fortunate to be leading the team when the Committee on Climate Change made the recommendation that we should meet net zero, and metaphorically a whole bunch of policy people came to me and said, is it actually, are they speaking through their hats, or is it actually technically feasible to do this? And so my team's biggest task that we did was actually marking the CCC's homework such that the government could agree that we should meet net zero, that we could meet net zero, and were able to legislate accordingly. Was one of my proudest moments. I think the biggest thing to say from a government point of view, it's pretty obvious really, but it's worth repeating, is that what's the change between the 5th and the 6th carbon budgets? And for those of you who aren't familiar, carbon budgets are the way that we legislate to reduce that legislates what our reductions in emissions should be until we meet our final target. And since setting the last budget, which was the 5th budget, we're now setting the 6th carbon budget, where the CCC will be making a recommendation, and the government of the day will either be accepting or rejecting that recommendation. We haven't chosen to reject one yet, but there's always time. And the choice will be, the difference between the 5th and the 6th one is now that when we set the 5th one, we had a target of meeting 80% reduction by 2050, and now we've got the net zero target. We have to decarbonise to net zero by 2050. They might say, well, what's the difference? Well, the real difference is that there's nowhere to hide now. You cannot be a sector that says, yes, all those other sectors can actually decarbonise because we're going to be part of the 20% that doesn't need to decarbonise. Now, you can imagine how many different groups of people said that we're part of the 20%, and you could add all of that up and it would flip the coin around to say that all of the people who added up to say that they were part of the 20% became part of the 80% who had to decarbonise. Anyway, that's changed. The nature of the conversation that we're having with our policy development teams has actually changed completely as a result of that. The second thing I was asked to make some observation about is why and how modelling helps. Well, certainly within the Department for Business, our department, BEIS, we use these large-scale energy systems models to think strategically about the choices that we have about how to decarbonize over time. And they do two things. One is that they allow us to look at particularly valuable assets such as biomass or hydrogen, and looking at where those capabilities are best deployed within a future configurations of our energy system. If we the risk is that leaving that to chance and trying to add that all back up by sectors is that you'd find that very scarce resource of biomass being used 3 or 4 times over, and only really notice it once you've actually added it, once everybody baked it into their plans for the future. The second thing that we set strategically using set the pathways using large scale, what I call tier 1 strategic models like NISMOD, and we use a version of TIMES to think about the long-term pathways. And then we ask the subsidiary models that are at sector or a tier 2 or more geographically dispersed to say what and how that could happen at a sectoral level and to kind of provide some kind of validation. The second thing to do you asked about what pitfalls there might be. Well, I think one of the biggest things that we see is that sometimes people get so enthusiastic about the kind of value of energy systems models, they forget about one, that these are essentially thought experiments. The second thing to say is that they often treat what we say as being forecasts rather than as thought experiments, and always bearing that in mind when you're trying to speak to somebody who isn't as well versed in modelling is a really, really important thing to do. And then finally, some of the differences that we're observing are quite small relative to the various amount of uncertainty that we see, or that we possibly like to see in the future. And the last thing that we struggle with is to think about the role of innovation. And we've seen through the deployment of wind how much the cost of offshore wind and wind in general has actually come down. If only we could understand what's going to happen for any of the other technologies, we'd be laughing. What's there? One other thing I was going to say, anyway, I'll stop there. I think oh yes, there was one other thing that I think is fundamentally important and really important for anybody who is thinking about speaking with government to think about using mathematical models, is to pay attention to the analytical quality assurance that goes along with anything that government does. There's a publication on this called the Aqua Book, which you can look at, and you can look at my department's approach to assurance, and you can bet your bottom dollar that if you speak to me or any one of my colleagues, that they will be asking you how you've actually assured that model such that it that it validates and verifies, so that it actually does what you intend it to do, and it does it without making any mistakes. I was really interested in the observation, just speaking about the presentations, really interested in the observations about how you saw the balance between electrification of transport versus the use of energy in the homes. I thought that it was the conclusion that you were drawing that it was cheaper just to go for all electric in vehicles was really interesting. I think I've got that right. What I was interested in was how you were treating the feedback loop in terms of cost, and the other thing that I thought was interesting was how you were going to treat and decarbonize particularly heavy goods vehicles under an all-electric strategy, because I understand the battery density that's required for really heavy goods vehicles is such that it's very difficult to get them to operate under an entirely electric mode. I think, oh yeah, and the last thing that I was interested in for these particular models was we're now thinking about the 6th carbon budget and what the strategy should be. The really important thing for us is to understand, under a whole variety of different possible futures, what we need to do now that will buy us optionality and time for the future. So what happens if carbon capture and storage doesn't work? What happens if it turns out that making hydrogen's 3 times more important, that it's more costly than we thought it was? But under those conditions, what do you need to do now that will help us to get to the point where we've got optionality and security that we know that we can meet our decarbonisation targets? And on that note, I'll probably stop, Jim, if that's okay.
That's great. Thank you very much indeed, Alec. Lots there in those remarks, and that question around what we do now to keep our options open is a very good one. I'd also say it's probably a rather costly one too. You don't get optionality for nothing. Over now to Siobhan Campbell from the Department for Transport, Deputy Chief Scientific Advisor. Siobhan, thanks very much for your time this afternoon. A few remarks from your perspective.
Hi, thank you very much, and thanks for the presentation. As Alec said, it's fascinating and really relevant to us. I think kind of from a transport perspective, we've always been on the side. We've had a completely self-contained energy system that's dealt with us, and so we've managed to kind of stay away from the whole wider energy system till now. And now we're facing the reality of being completely integrated into the energy system and being a key component of it. So I think it's really, really important that we get this kind of modelling done and this systems approach. So we welcome it hugely, and we'd very much like to engage further with it. I've been asked to talk about kind of, well, what is the role of transport in net zero? And as was said right at the very beginning, we know that transport is the worst the biggest contributor to UK carbon emissions now. We know that in terms of the progress over the last 30 years, we've pretty much flatlined from a transport perspective, that we haven't been going anywhere. A lot of that is to do with increased demand as opposed to increased emissions. So vehicles, especially road vehicles, are becoming more efficient, but yet there is a problem here. And I think it's very interesting, and it's interesting that the model's been trying to deal with this as well, that there's therefore both a technological and behavioural aspect to this, and we need to be tackling both of them. And the Committee for Climate Change has been very clear on that as well, is that you're not getting here without bringing the population with you. And so it's really interesting to see how you've been factoring that into the modelling. From our perspective, the department is incredibly committed to this. It's the number one priority across government. I mean, levelling up and decarbonisation are the two priorities that kind of follow COVID and Brexit. So kind of there's quite a lot of priorities, but in terms of policy priorities, decarbonisation is it. And I think there's a realisation and an acceptance of transport's role in this, not just because we're the biggest emitter, but also if you look at how we're going to get the rest of the way to net zero, transport then becomes actually relatively easy compared to some of the other things. And one of the things our director responsible for this has been saying is, you either decarbonise transport or the population becomes vegan. I mean, there are some really difficult choices to be made here, and then transport then starts to look more attractive and more have more potential for decarbonisation. It was interesting to see some of the things presented today. I think, as I said, the systems approach is really important. On hydrogen, it's really interesting just how Marmite it is actually in practice. There seems to be kind of lots of real advocates for hydrogen and people that don't get it. Primarily, as I understand it, from an economic perspective, that the economics of hydrogen will really not stack up very well toward against an electric car. When you start getting bigger, and what we've been thinking about hydrogen for is hydrogen has a real role in these hard to decarbonize modes. And so you're looking at your kind of HGVs, you're looking at maritime, you're looking at aviation, and there probably is something here. However, again, back to the systems perspective, if hydrogen has currency and prices start to fall, and then it has the potential to become more attractive. There's definitely an issue around can we put batteries in everything and suddenly electrify, not suddenly, but kind of electrify absolutely everything? Do we have the capacity, both from a network perspective, but also from a production perspective? And therefore, does hydrogen have a role to play there? It's something that we really are trying to get to the grips of. So rather than keep saying it's a Marmite issue and there's no clear answer, actually let's do some development, let's do some testing and get some results that can then feed back into modelling. one of the things I think is really interesting, and your model doesn't account for it because it can't at this stage, but there is real uncertainty now about what's happening to transport post-COVID, and we're seeing big changes, especially to commuting behaviour. Our social research suggests that we might be heading for a complete rebound on leisure transport. People want to go back to doing the things they did before for leisure, but actually are we fundamentally changing our commuting patterns because of this big shock to the system? And I think it's really interesting what that will do to demand, and especially that kind of peak demand. Two final points that I'll make before I wind up. One is around, I think there's a real benefit of, we have a national transport model that we use within DFT, and I don't know what engagement you've had with that. I know we certainly have just had delivery of a version 5, which has more kind of national networking and more zoning, and I think there's definitely be good to kind of work and join up on these two. And the final thing is around freight, and freight's really hard for us. We are again trying to kind of really lean into this area because it's particularly difficult, it's particularly important, and we have had criticism as a department on freight before as well. But one of the issues is there's a real paucity of data on freight. We don't really know anything, and so therefore it's very difficult to model. It'd be really interesting to know whether you've got some novel sources in there. That's all I'll say on that.
That's great. Thanks very much indeed, Siobhan. And you've picked up on a number of very challenging areas around representation of transport. And some of those I'll pass back to Simon in a moment in the discussion. But before I do, let me now welcome Nick Eyre, also from the University of Oxford and leader, as I said at the start, of the Consortium for Research on Energy Demand Solutions. And Nick, if I may, there's been a series of questions in the chat about questions of energy demand, and in particular building energy demand, from Daniel Scharf around zero carbon homes, from Gavin Hillip around energy efficiency and the assumptions we've made around that, from Ken Alsford around building ventilation and heat efficiency, from and then an interesting question from Adam Brown about recommendations for local areas and how policy should be developed at a local scale. There's a lot for you to take on there, but welcome any thoughts from you, Nick.
Thanks, Jim. And most of the people who you've just named I've worked with at some point in the past, so I won't address all those, but I will address the bigger point. I mean, I think it's probably worth saying that I did work on the ITRC Consortium until 2017, which gives me the advantage of knowing what about the work that Simon and Madassa have described, but also to see how much it's improved. And I think it is worth saying we are in a very challenging time for, I mean, I don't need to go into details because other people have said this, but the challenge of modeling our path to net zero. We certainly need to look more at systemic interaction, particularly between the transport and energy systems, for the reasons that Siobhan set out. Even with mass electrification, we're probably going to need some new vectors. Hydrogen's been mentioned, but also potentially heat as a vector as well. And as the detail of the modelling that Madassa set out shows, hydrogen can come from different places with very different implications for the energy system. The other two changes which Simon and Madassa sort of assume in their modelling, but I think is worth flagging as being hugely important compared to traditional energy systems modelling, is the importance of better time granularity and better spatial granularity. Now, if you take all those challenges together, you're very unlikely to see a single best model develop. And I mean, Alec pointed that out, that actually they and other policymakers use different models for different purposes. So I think my answer to some of the questions that have been raised about buildings is, well, the NISMOD is not going to compete with the National Household Model on the detail of improving the efficiency in buildings. It's not going to compete with the National Transport Model that Siobhan mentioned for an all singing, all dancing transport sector model, because it's trying to cover more areas. NISMOD as it stands makes some behavioral assumptions in different scenarios, but it doesn't attempt to model where those different behaviors come from. And I think it would be a mistake for an infrastructure model to try to do better at modeling behavior than people who spend their lives modeling behavior. So I think it's really a call for models with different strengths to work together. Having said that, NISMOD has some huge strengths, and it has two in particular. The first is this focus on system of systems, the way that different systems interact with each other. And in other seminars, I know Jim and colleagues will have talked about other areas, but in this case, the interaction of transport and energy is absolutely critical to getting towards net zero. And I think NISMOD is making great strides there. The second is the extent of spatial disaggregation. Some of the energy system modelers that Alec talked about treat the UK as a single point, essentially, and that's fine for some things, but it isn't if you want to understand where and when different bits of infrastructure need to be will need to be built. So those are really the strengths that the modelers that have been talked about this afternoon have got, and that's where I think they are making big progress. I think what struck me is the discussion of heat and transport together. We think those are, of course, probably the two critical areas and most difficult areas to decarbonize. There's huge similarities in terms of a probability of large electrification, but also possibly some other vectors. But huge differences, and the important aspect of transport, which comes out of the work that Madassa described, is its ability to act as an energy store because of the storage capacity of vehicle batteries, and that isn't mimicked in the heat sector at all. And so transport has this potentially important role in the energy system that's not really been important in the past, because fossil fuels provide lots of storage, but that will be important in future. Having said that, it's limited. It's not going to address the seasonal mismatch in heat demand, and so we're probably going to need to look at other forms of seasonal demand response or seasonal storage. My answer to some of the questions you pointed out, Jim, is, well, this probably isn't the right model to do those calculations in, but certainly those issues need to be addressed and need to be brought in to the NISMOD framework through some sort of soft linkages. I'll leave it there.
That's great. Thanks a lot, Nick. Now, everyone, I'm conscious of time. With these webinars, we've said that we have a hard end at 1/4 the hour, and we've, depending on the amount of discussion, have finished sooner or later relative to that hard end. There's a lot of questions here, so I think if you'll permit us, we will go past the hour by a few minutes. I'll try and carve up those questions now. But first, I should also note that Sven Egeman, who developed the energy demand model, is with us today, and Sven has actually been answering a number of the questions in relation to that energy demand model, which Nick referred to as well. So thanks very much indeed, Sven, who's now left our group in Oxford and is actually in Zurich. So welcome back, Sven, and thanks very much indeed for responding to those questions. So first I'm going to go to Simon with a clutch of questions around the transport system. And as Nick hinted in his response, some of these are well beyond the scope of NISMOD, but as a transport specialist, I think you'll be able to respond nonetheless. And I'd say that I divide them up into two packages. Basically, there's a whole bunch of interesting questions around the behavioral aspects of demand and the role of regulation in there. And then there's some questions about the fleet. And so on the demand side, there was a question from Gavin around the assumption of price elasticities and the extent to which reducing electricity prices would and the shift to EVs would increase demand. There was a question from Daniel Scharf around the impact of speed limits and the potential impact that could have. There was a question from Darren Robinson about mobility as a service, the effect that might have. And indeed, there was the question from Siobhan, if we're talking about demand, about the potential permanent shifts that might occur around COVID, and from Pierre Victoire around degrowth. So there's a meaty pile of questions around transport demand, but that's not it, Simon. If you can keep track of all of this, because there were also questions from Gavin around vehicle efficiencies, from James Dixon and Christian Brand as to whether hydrogen vehicles are actually realistic at all. And there was Siobhan's question around, and indeed Alec's questions around freight. And finally, Karen Day, a question around marine and what we do about that. So a whole bunch of things. Respond as you wish, Simon. Thank you.
Well, how many hours have you got, Jim? Okay, I'll try and get through them quickly. So starting with the behavioural ones. So Gavin, you mentioned about price elasticities. So it's not quite as simple as to say that as cost falls, demand will automatically rise, but there is an element of that in the behaviour which the model simulates. So we do have a negative cost elasticity. So if cost goes up, demand falls and vice versa, but that will be attenuated by some of the other elasticities in the model relating to things like population growth, journey time, and things like that. So while a reduction in the price of fuel might reduce cost, if that then led to increased congestion, that would then increase the time cost. So you won't get a simple linear trend of growth there. The question about the impact of reducing speed limits, I think that was saying, well, if you reduced speed limits to 50 miles an hour, would that improve fuel efficiency and reduce congestion? We could certainly look at modelling that. I think probably the model could cope. We just have to double check the equations linking speed and fuel consumption for electric vehicles, but that could help. One of the kind of limitations of this kind of work is it was more focused on energy, and therefore we did keep the number of transport scenarios quite small, but obviously there's a huge number of different variants you could look at here, and that's something maybe for future work. Mobility as a service, so I think that was around saying if people are purchasing the use of vehicles rather than the vehicles themselves, will that impact demand, intensify the use of a smaller number of vehicles? Yes, it might. If you're looking at actual vehicle sharing, then that would reduce traffic. So multiple people sharing a vehicle for the same trip. We can look at that up to a point, but we haven't done so far. If on the other hand, you mean different people sharing the same vehicle but using it at different times, that wouldn't look probably that different in terms of traffic, but it would have implications for the use of vehicles for energy storage. So that's perhaps more something for the energy model, but that is a good point. COVID, yeah, we did these runs sort of quite early on in the stage in the COVID pandemic. and deliberately didn't attempt to take account of any possible COVID impacts. But I think you're undoubtedly right. I mean, there could be some really quite profound changes in work behaviour which could impact on travel. How helpful that will be in terms of decarbonisation, I don't know, partly because I suspect quite a lot of the trips that will no longer be made are the ones which are actually easier to decarbonise, as in trips on flows into major cities. So whether it helps or hinders, I'm not sure, particularly if people substitute their work trips with new leisure trips. And there is some evidence suggesting that could happen when you look at travel behaviour more broadly, and that people will tend to allocate a certain amount of their lives to travel. And if that travel isn't for work, well, maybe they'll make more leisure travel, which is then harder to actually decarbonise easily. But yeah, so obviously COVID is a big unknown in all of this. And then the final one was around degrowth, I think. So again, I think this is sort of the question of whether there might be a reduction in trip rates over time, which again is something we can model in our system. We haven't for this work, but we did include that in the work we did on decarbonisation strategies for the England's economic heartland, and we did look there at some sort of behavioural shift as a means of helping with decarbonisation. And if you can get that to happen, then we found that could actually be one of the most beneficial measures out there, perhaps unsurprisingly. Right, technology, and apologies that I am dashing through these, but so vehicle efficiencies, I am trying to find where that question came up, so I can't remember exactly what you were asking. Just bear with me. Oh, okay, so we have assumed some improvements in vehicle fuel efficiency in these strategies. We have only included a single trajectory, again, just to make it easier to pin down the causal links in the results we're getting. But obviously that could have potentially quite a big impact, and that is something that is easy to tweak within our model inputs. On the hydrogen question, I thought Siobhan put it very well when she said that it's a bit of a Marmite issue, and I would entirely agree there. So I'm not in any way an expert on vehicle technology, but I've talked to quite a number of people about sort of potential futures for transport energy sources, and it does seem to vary hugely. So you'll talk to one person and they'll tell you that hydrogen is in no way credible, there's no possible way in which hydrogen is going to be useful. But then you'll talk to someone else, they'll say, well, actually it's really the only viable option for a lot of these things, particularly things like heavy goods vehicles, and if it was given a bit more attention, actually it has far more potential than electricity. I don't know enough to come down on either side of the argument, but it does seem one of the big areas of disagreement in this kind of field at the moment. And then the questions about freight, I'm afraid we don't have much of an answer there in terms of better data. We have been relying on pretty much the same data sources as the DFT will have been using in its modelling, I imagine, given that we are using DFT freight data by and large. And I have talked about this a fair bit with one of my colleagues at TRG, who's an expert in freight transport, and his view is the same as the one we've heard expressed previously. The data just isn't really there. So perhaps collecting more reliable data on freight transport and freight movements should be one of the priorities in improving modelling in this area. Oh yeah, one. So then marine transport. So we haven't specifically considered maritime in this work because we were looking at primarily domestic transport. I'm afraid I'm not really the person to ask about decarbonisation options, but I would suspect that hydrogen, as someone mentioned, is likely to be one of the most obvious routes to go down. I know even things like moving towards more conventional gas power for shipping could be helpful, just because traditional maritime bunker fuels are so heavily polluting that even shifting to gas would give you quite a benefit in terms of decarbonisation, even though it is still a fossil fuel. But as I say, I'm not the expert there. Right, Jim, have I covered everything? Sorry, that was very rapid.
That's a fantastic job you've done there, Simon. A couple of remarks on marine shipping, both from Alec, who mentioned ammonia, which is a very good point, and from Siobhan around hydrogen. There's a clutch of questions for Madassa, and then I think we will have to draw things to a close. But I put out a final invitation that we do have two extremely knowledgeable civil servants with us. So if you have a final question for the government, then by all means put that in the chat. But before I do that, Madassa, not quite as many questions for you as there were for Simon, but still
Good.
some very different ones. A question from Ash Gupta about the distribution network and the implications of all of this V2G and electric heating for the distribution network. A question from Graham Phillips to do with an extreme version of weather variability, the beast from the east, and how much capacity we would need to cope with weather extremes like that, where one has very low wind and extremely high heating demand. And then a couple of questions which I think you'll agree are probably outside our scope, but you might wish to comment on, both from Brian Love about embedded emissions in the materials of electric vehicles, and from Sebastian van Dort in terms of the technology costs for V2G vehicles. But over to you, Madassa.
Okay, Jim, I'll just go down the list. So the question from Ash Gupta. Ash, you're absolutely right. There's a huge amount of, especially on the all electricity strategy, huge amount of heating and transport that would be electrified. And we have to start making decisions in the 2020s. So this is really one for Ofgem to make it happen, to make sure that systems are in place, to make sure investment can be made, to make sure that the distribution system is ready for this large influx of electric vehicles and heat pumps on the system. There's a question on what policies you would recommend UK local areas, cities, district councils. Again, this is a difficult one. You would have to, I mean, each local area would have to look at the local economy, look at the industries that you have. Can clusters be built around various industries and connect to other parts of the local system? So especially I'm looking at with hydrogen and CCS, you would look at a cluster and then connect that from that. But you would need grants, you would need skilled engineers, you would need performance compliance of new homes, etc., retrofits. So essentially it's down to funding. So the funding needs to be made available, and in this post-COVID world it looks quite difficult as you look forward. There's a question on BECCS, and if we assume BECCS, we did assume BECCS. You probably couldn't see it on the diagram because it was quite small. So we have we do have quite a large capacity of BECCS in the system, which mitigates some of the emissions. There was a question about peak gas load, which could rise up to, was it 250 gigawatts during the Beast of the East storm. And I guess this is in reference to the all electricity strategy. Within that strategy, we had approximately around about 290 gigawatts of capacity in the system. We assumed heat pumps had an efficiency of 2.5. And we have hybrid heat pumps that could take a bit of the load off, so gas is used instead of electricity. We had demand reduction in that strategy, so efficiency in homes up to about 25% reduction. And we had other sorts of capacity on the system. We had 10 gigawatts of grid storage batteries. We had V2G around 10 gigawatts. We have nuclear on the system, and we have interconnectors on the system. So if you combine all of that together, I'm pretty confident that we could actually meet this big increase in heating demand during that type of scenario. And there's a question on V2G as a business case, and what kind of assumptions I guess we made regarding assumed consumer behavior. Essentially, what we assumed in the managed smart charging cases is the optimization actually takes over. So what the optimizer tried to do was to minimize costs over a particular day or a couple of days. From the transport model, what we did was we looked at the number of trips each hour. So this is the energy demand or electricity demand for electric vehicles. That gave us kind of an estimate of the number of vehicles in a particular location. And from that, that minus the electricity demand gives an idea of how many vehicles were stationary, and then we took a percentage of that allowed for B2G services. So that's how actually it fed into the model. What other questions are there?
I think you covered them all off pretty well then.
Yeah, I think I've covered most of them.
Thanks
Okay.
very much indeed for that. We're practically out of time. We've still got 61 people with us, so that's a fantastic showing. Let me thank all of our presenters once again, Madassa Chowdhury, Simon Blaney, Alec Waterhouse, Siobhan Campbell and Nick Eyre for their contributions. I'm just going to share my screen again. Hopefully you can see that, to remind you that this webinar series continues for 3 more webinars. The one next week on the 28th of October is looking at all of the work which the ITRC has done on risks to infrastructure networks, climate-related extremes, but also there's been work on security hazards and indeed space weather, and how we've been able to model the systemic risks, the interdependencies, and how those impacts cascade potentially through into large risks for the economy, but then how we can use system of systems analysis to design and prioritize adaptation options. And that work relates to analysis that's been done in the UK for the National Infrastructure Commission and others, and also internationally for the World Bank and others. On the 4th of November, we're looking at the analysis which ITRC and others have done on resilient water supplies, a focus on England and Wales for that modelling, and also some analysis of interdependencies with the energy sector. So if you're interested in the resilience of cooling water supplies for energy, then that's part of what we're talking about. And then finally, on the 9th of November, we will talk about digital technologies, both fibre and 5G, and the work which ITRC did on analysing those options for the future. So a lot still to come. Thank you very much indeed for joining us today, and we look forward to seeing you again for the coming webinars. Bye-bye.